Okay, welcome back. We're working on finding the discrete time Fourier series, and in this example we're going to find the DTFS of this simple little square wave that alternates between 0 and 1. Now there are two parameters that describe this square wave, n1, which defines the pulse width. So the pulse width is 2 times n1 because you have n1 samples to the left, n1 samples to the right, and then the origin. So 2n1 plus 1 is the pulse width, and then the other parameter is the period, capital N. So that's how many samples it takes to repeat, as usual. So I've shown here with n1 equals 2 and n equals 8, but we're going to keep those parameters and we're going to keep them through the calculations. All right, so I need the Fourier series. So I'm going to start with the definition of the Fourier series. This is not sines and cosines, so I have to use the analysis equation. I cannot simply break them up immediately into complex exponentials. So we are going to just write out that formula. This is x of n. I should state that. E to the minus jk omega 0 n, and I want to remind you that omega 0 is 2 pi over the period n. Okay, so this was the analysis equation. Remember, give me x of n. I'm going to analyze it for the AKs. Now, I need to sum over one full period. And for mathematical convenience, I'm not going to go from 0 to n, because then I have ones, and then I have zeros, and then I have ones. What I'm going to do instead, the period that I'm going to choose is more like something like this. I'm going to start here at this sample and then go to this sample. That way I avoid this alternating between 0 and 1 and then back to 0 when I just go from 0 to 1. This will be more clear in just a second. So I'm going to say 1 over n, and I'm going to go from n equals, whatever this is. I guess I'll still keep it as a period. Actually, let me back up. So now in this red window, the only non-zero samples are from negative n1 to n1. So my sum, I'm going to take from negative n1 to n1. You see, I'm actually going over a full period, which is the red to the red, but these zeros contribute nothing to the summation, so all I really need to do is go from negative n1 to n1. And in that range, our signal is just 1, so I'm not even going to write it. So I have this. Okay, so make sure that that sits well with you. Okay, and now I need to evaluate this summation. Well, I have a couple of choices, the finite sum formula and the infinite sum formula, but I need to get a 0 here to use those formulas. The lower bound needs to be a 0. So I'm going to do something that we've seen before in this class called a change in variables. All right, and I'm going to just choose a different variable, m, and I'm going to let it equal n plus n1. I'm going to let it equal whatever I need to add to get a 0 here. So when I change the variables, when n is minus n1, then m is equal to 0. That's what I wanted. And then when n is equal to n1, I get 2n1 up there. And then to finish the change in variables, I need to replace the n here with m minus n1, right? Now, using properties of exponents, I can bring out a factor, e to the positive j k omega 0 capital N1, because that does not depend on the indexer m. So that can come out of the summation. And I'm left with that. Okay, now let us recall the finite sum formula. So I'll write this down. The finite sum formula. Okay, it states that if I have a sum from n equals 0 to n of alpha to the n, that's equal to 1 minus alpha to the n plus 1 over 1 minus alpha. Okay, so we compare that finite sum formula to what we have here. Our indexer is m, our upper bound is 2n1, and our alpha here is e to the minus jk omega 0. So that is in the correct form. That's in the form that we need. So I'll just rewrite this. This is e to the jk omega 0 n1 over n. Then applying this formula, this is equal to 1 minus e to the minus jk omega 0, that's alpha, to the upper bound plus 1, 2n1 plus 1 over 1 minus alpha. Okay, so we've evaluated that sum. Now, notice that when k is equal to 0, we have an issue. When k is equal to 0, e to the 0 is 1, and so we have this denominator is 0. And the numerator is also 0. So this does not apply when k is equal to 0. Okay, so we're going to come back to that, but let's first find the k equals 0 term. So let's now that we know that k equals 0 we have to handle separately, let's go back to the before we applied the finite sum formula, so that's over here, and let's immediately plug in 0 for k. So I'm looking at this right here. A0 is 1 over n, e to the 0 is 1, and then a sum m equals 0 to 2n1 of 1. So what is that equal to? Pause the video to think about this. The answer is, well, if I add 1 to itself, well, how many times am I adding 1 to itself? I'm going from m equals 0 to 2n1. So because I'm starting at 0 and not 1, I'm actually adding 1 to itself 2n1 plus 1 times. So that sum is equal to 2n1 plus 1. And so we get A0 is equal to 2n1 plus 1 over n. Further, because the discrete time Fourier series repeats every n times, this is also a Rn. Okay, so if n is equal to 8, this is also A8, A16, A24, a negative 8, a negative 16, a negative 24. They repeat every 8 times. All right, so we've got A0. Now let's come back to this here. Now, this is the answer, technically, okay, but it doesn't look good and it's very hard to interpret. So we're gonna work on this a little bit, and this is not something that I would expect you to be able to do without a hint. But I'm going to show you. I'll show you the hint. I'm going to show you the process so that you can see this. There's actually a sine wave hanging around here somewhere, and we're going to try to find that sine wave. Okay, so we have, first of all, this e in here, and I'm going to distribute this e in to the numerator. All right, so I'm going to say that ak equals 1 over n times. So when that e comes in, I've got e to the j k omega 0 n1. And then when it comes into the next term, notice I have a minus jk omega 0 2n1. So that makes a minus jk omega 0 n1 plus 1. one of them goes away, and the denominator stays the same. Okay, like that. Now, I claim that there's a sine wave here. Well, for a sine wave, the exponents have to be the same. You see, we almost have it. We have e to the something minus e to a negative, but that power is not the same yet. We have n1 here and we have n1 plus 1 here. What the trick is to split the difference in the exponents by factoring something out. So again, this is not something that I would expect you to do, all right? But in the numerator, I'm going to factor out e to the minus jk omega 0 over 2. That's what I'm going to factor out. I would not expect you to know how to do this on your own. So now, having done that, this guy is e to the jk omega 0 n1 plus 1/2. Okay, now let's check. Why is that? Well, let's distribute it back in and see what happens. So here I've got e to the jk omega 0 n1, okay? Then I've got e to the jk omega 0 1/2. And so when I distribute this in, I've got negative that, and so they cancel and they make what I started with up here. Minus, so that looks good, e to the minus jk omega 0 n1 plus 1/2. Okay. Again, if you want to check that, just distribute this back in, and you'll see that now they add together to make this 1 here. So I haven't changed anything in the numerator, and in the denominator, I'm going to factor the same thing out. Here's the trick. So what do I have in the denominator? Then I have e to the positive jk omega 0 over 2, right? So they cancel and make 1. And then I have e to the minus jk omega 0 over 2. And so now the signs work together, SIGN, and they add up to 1. The fractions go away, and I get the same thing back. Again, pause the video if you need to convince yourself that when you distribute this back in, you get this original expression. So now these guys cancel, right? We pulled the same thing out of the numerator and the denominator. And if I can put a 1 over 2j in the numerator, and I can put a 1 over 2j in the denominator and not change anything. And so what we get is the sine of 2 pi k n1 plus 1/2 over n. So I'm making this substitution as well. Omega 0 is 2 pi over n over the sine of k pi over n, right? And so that is the Fourier series coefficient. Those are the Fourier series coefficients when k does not equal 0 or plus or minus n or plus or minus 2n and so on. Right, I should add that over here because this was the case for those k values. Okay, so now we've got some signs. So what does this mean? Well, first of all, notice that it's purely real. The AKs are purely real. So we could plot them if we wanted to. You can just plug in some values of k, n1, and n, and you get a real number, and you can make a plot of this. And it looks like, I'll just plot it really quickly. It looks something like this. Here's 0. Okay, this is just a quick sketch of it. You can use your favorite plotting software to be able to plot that. But this is what you get. And so I want to point out that we have a periodic AK. It has to be periodic with period n. Okay, all of the discrete time Fourier series are periodic. So you can again, I drew x of n with these parameters. N1 is 2 and n is 8. So you could put those in here if you wanted to. Okay, and then you can plot it versus k, and you can come up with this plot on your own. So I do want to point out one kind of way to check our answer. We said that the pulse width of this thing was 2n1 plus 1, and the period was n. Now notice if that pulse width approaches the period, that is to say, if the entire pulse width takes up the period, meaning the signal becomes just constant at 1, right? If the pulse width takes up the entire period, then the signal is constant, 1. So let's investigate what happens in this limit to our answer. So first of all, the A0, and the AN and the A2N, etc., equals, in that limit, when 2n plus 1 becomes n, notice those guys go to 1. Those guys go to 1 in the limit. Yeah, well, that makes sense because remember A0 is the average value, or it's the DC. So again, in this limit, when the pulse width becomes the period, then we have a constant signal at 1. So that makes a lot of sense there. Very good. Now let's notice what happens to our AKs when k is not an integer multiple of the period. In that case, I have, if I make the substitution that 2n1 plus 1 is equal to n, then in the numerator, I get the sine of the sine of k pi, it looks like. Okay, let me back up. Let me show you the steps. Let me show you the steps. So if I put in 2n1 plus 1, so let me rearrange I'm just looking at the numerator right now. 2 pi k, let me get a common denominator so I can add these. 2n1 plus 1 over 2 over n. Right? So this is just the numerator I'm looking at. So I'm saying in the limit now, so this numerator in the parentheses becomes n. That cancels with this n. And so this becomes the sine of pi k. The numerator becomes the sine of pi k. So what's the sine of pi k? For any k, the sine of pi k is equal to 0 in the limit. So the other AKs go to 0 in this limit, k not equal to 0, plus or minus n, plus or minus 2n, and so on. So what does that mean? Well, again, remember, why is this limit so interesting to us? Well, this is because in this limit, our square wave becomes a constant. And so in this limit, we're saying the harmonic components go to 0, that there are no oscillations. And that's exactly right? For a constant signal, we should have no oscillations. So we should have no oscillations, and we should have a constant value of 1, and that's exactly what our answer is telling us.